Hi, everybody. Let's continue talking about the applications of what we learned about gravity and Newton's three laws of motion to understand some astronomical concepts. I left off in the last video about to start talking to you about orbital velocity and escape velocity. This is the most rocket science-esque lecture that you're going to get all semester. So if you're interested in rocket science, here are the fundamental concepts that you need to know. I'd like to start our discussion on orbital velocity by going and doing a thought experiment that Newton himself did. This is called Newton's cannon. What I want you to do is picture that we're going to put a magical cannon on top of this giant pedestal on Earth. So at first, we're going to operate this cannon as if it's a normal cannon. We'll put our cannonball in there. So load the cannon, and then we're going to fire the cannon. And we just noticed that the cannonball would go out and it would plop down on the Earth. It would take a parabolic path and gravity would pull it down because here we are on Earth experiencing Earth's surface gravity. Everything is being pulled towards the center of the Earth at 9.8 meters per second squared. So as the ball launches out, it gets pulled down to the surface of the Earth and plops down. Okay. No surprises there. We've all probably thrown a ball and watched it go forward and then fall on the ground. All right, so let's up the power of the cannon. We know that the Earth is round, and this is one of the reasons we know the Earth is round amongst many, 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 many others. But we know that the Earth is round, so we fire a cannonball with much more power than any cannon that currently exists. Actually, that's not exactly true, but we fire a cannon with a whole lot of power, and this time we see it go forward, and it's moving forward really, really fast because we launched it really, really fast. And it goes, it travels, and it falls beyond what we can see at our horizon, but it still plops onto the surface of the Earth somewhere really, 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 really far away. But you can see that it started to fall, and it went a little bit further in this view than you'd expect it to because of the curvature of the Earth. Now let's really ramp up the power of this cannon. Let's keep doing this. We'll fire a cannonball after a cannonball after a cannonball. We can go a little bit further each time. Eventually, we would hit this balance point, this perfect velocity to launch the cannonball at. So it would come out of the cannon, it would fire, and it would be falling towards the Earth with an acceleration of 9.8 meters per second squared. But the Earth would be curving away from it at the exact same rate that it is falling down. So it goes and it's falling towards the Earth, but the Earth is curving so that it always remains the same distance away from the surface of the Earth. So in that case, it would fall towards the Earth, but keep missing, fall towards the Earth, keep missing as the Earth curves away, and it would come back around and you better duck or that cannonball is going to whack you in the back of the head that you launched, assuming no air resistance. So in this case, at just the right velocity, we fired the cannonball and it's falling towards the surface of the Earth, but it's forever missing. I mean, one could say that the secret to flying, or at least Douglas Adams said the secret to flying is to throw yourself at the Earth and forever miss, which technically, that's the secret to orbiting. So when you fire a cannonball at just the right velocity, you launch something at just the right velocity so that it falls and it's falling such that it's just curving around and forever missing the Earth. You've essentially put something into orbit. The question is, what is this perfect velocity? This velocity that puts something into orbit. It's what we call orbital velocity. And the way we can figure that out is we just have to balance out two different forces. We have gravity pulling things towards the Earth, and then whenever you have something that's rotating around and around and around, moving in a circular path, I just put a ball in this bag right here. So if I spin this bag around and around and around, I feel like there is a force that's trying to pull the bag. So if I let go of it, don't break stuff at home, it goes flying off. Why was it able to move in that direction? Well, it was feeling this force related to spinning around in a circle called centripetal force. A force that is an apparent force, it's not a real force. It's something that comes out of things that are moving in a circular path and then balancing that out with Newton's laws of motion. but you can feel it. This is also why you probably did this as a kid, or some of you did this as a kid, with a merry-go-round, also called the playground death trap, where you get a merry-go-round and one of your friends spins it around as fast as they possibly can, and you hang onto the edge for dear life. What happens? Your feet go flying outwards. What is pulling it so your feet go flying outwards and you're hanging on for dear life, trying not to slip off and get chucked away from the center of the circle? Centripetal force. So let's take the centripetal force, which is trying to move you away, or if you're moving around in a circle, it's trying to move you away, and balance it with what's trying to pull you in, gravity. I know that's not a great explanation, and it's beyond the scope of this course, since we haven't even gone through to talk about centripetal force. That's the topic for an intro physics class, but just bear with me for a second. Because I have the force of gravity here. That's just an equation. Hopefully you're used to seeing it by now. This is the equation for centripetal force. Notice that it has a velocity related to it, and it also has the radius. And here, if we're talking about the distance away from the center of the Earth. So if you're at the surface of the Earth, that would be the radius of the Earth. If you're 1,000 kilometers above the surface of the Earth, that would be 1,000 kilometers plus the radius of the Earth. And let's just set them equal to one another, cancel some stuff out, and then rearrange and solve for the velocity where these two forces, what's trying to throw you away from the Earth and the force is pulling you towards the center of the Earth, get them in balance so that you're not moving towards nor away, you're just orbiting, and solve for it, and you come out with this equation for orbital velocity. So we had to do some physics there, but essentially we came up with this velocity so that you can fall towards the Earth and constantly be missing it, a forever free fall, and that velocity is what we call orbital velocity. And it has this equation. It's the square root of that universal gravitational constant times the mass, in this case the mass of the Earth, divided by whatever height you're orbiting at, away from the center of the Earth. So if we're going to talk about, say, a satellite that is 1,000 kilometers above the Earth, we would take Earth's radius, 6,400 kilometers, add the 1,000 kilometers to it. All right, but I know that is a strange equation that you're looking at. It's the square root of gm over r. But let's look at what it depends on. And this is what I'd like you to know for this class. That as the mass of the thing that you're orbiting increases, as this number gets bigger, even though we're taking the square root of it, this number is still getting bigger, so the orbital velocity gets bigger. If an object has more mass, you have to move faster to orbit it for the same altitude above it, for the same height above it. Also, as you increase the distance, as you move away from the gravitational source, as r becomes bigger, I'm dividing by a bigger number, my orbital velocity becomes smaller. So the farther away I am from whatever I'm orbiting, the slower my orbital velocity. Oh, Copernicus, you got that right. You just didn't quite understand it yet. Planets farther away from the sun move slower. They orbit slower. Here's the math behind it. Here's the physics. As our distance away from the sun gets larger, the speed at which we orbit becomes slower. So increase the mass, you need a larger orbital velocity. Increase the distance, you need a lower orbital velocity. And here's a profound observation. Notice that in our orbital velocity, the mass of the cannonball, the mass of a juggling ball, the mass of the International Space Station, the mass of the moon orbiting the Earth, that was never a part of it. The mass of the Earth as it orbits the sun, that was never a part of it. The orbital velocity is independent of the object that's doing the orbiting's mass. That's pretty profound. That the mass of the Earth doesn't determine Earth's orbital velocity. If Earth's mass were to become 10 times greater than it currently is, 10 Earth masses, we'd still have the same orbital velocity. It would still take us 365.25 days to orbit the sun because we would still have the same orbital velocity. So I'm going to leave this question. I'm going to put it here and I'm going to briefly talk about it, but it's a good one to consider. This is getting deep into the concept. So let's take the planet Jupiter, about 300 times more massive than the Earth. If Jupiter orbited at 1 AU where the Earth is, how would Jupiter's orbital period change? What would its orbital period be? If we moved Jupiter closer to the sun, if we made this number smaller, it would be orbiting faster, which means it could go around quicker, so its orbital period would be smaller. In fact, it would have the same orbital period as the Earth. We could replace Earth with Jupiter, and Jupiter would still orbit in exactly the same amount of time that the Earth does. Because it only depends on, in that case, the mass of the sun, which is still the same, and the distance away from it, and we moved Jupiter to have the same distance away from the sun as the Earth is. So, orbital velocity. Let me give you some examples of how you might want to work with this, how you might see questions on an exam. So let's consider the moon orbits the Earth at a distance of 384,400 kilometers away. If the distance to the moon were to increase, how would the moon's orbital velocity change? If the distance to the moon, if this value, the distance, were to become larger, how would the orbital velocity change? So orbital velocity is inversely proportional to the distance. Inversely proportional to the square root of the distance, to be technical about it. But the distance increases, the orbital velocity would decrease. And I didn't put answers in here, so let's just go ahead and do something on the fly and add an answer box. So the answer box for this one is the orbital velocity would become smaller. The distance became greater, so the orbital velocity became smaller. All right, so this next one. Same question, but how would that change the orbital period? So if the orbital velocity is smaller, it's moving slower. It's also technically not only moving slower, but it's going around a bigger orbital path because it's farther away. But it doesn't matter because it's moving slower. So if it's moving slower, it's going to take it longer, right? So its orbital period would become longer. And there we have our answers. And now let's talk about taking this concept to the extreme, so-called escape velocity. Orbital velocity is great for putting satellites in orbit around the Earth. Our GPS satellites, our geosynchronous satellites, the International Space Station, all of that is governed. You gotta launch something and move it to the orbital velocity. So whenever you see SpaceX launching satellites or NASA launching satellites, then what they're doing is they're putting a satellite on a rocket, and that rocket's job is to change the whatever that satellite's velocity is to the orbital velocity for whatever altitude, whatever height above the Earth they want it to orbit. That's the rocket's job. You put that satellite at the orbital velocity for how high it is above the Earth, you have put a satellite in orbit. Rocket science. But what if we wanted to leave the Earth system forever? What if we wanted to go to Mars? What if we wanted to go investigate Venus and what's going on with this phosphine there? What if we wanted to go visit Jupiter? What if we wanted to leave and go explore the outer solar system? If we wanted to go see what's going on with Uranus and Neptune and these weird Kuiper Belt objects? Well, to do that, we would have to escape Earth's gravitational pull entirely. We don't want to be stuck in orbit around it. We want to leave and never come back. We want to escape Earth's pull of gravity. And to do that, you have to give something what we call escape velocity. So it would be, how fast would I have to throw this ball straight up in the air, or really the direction doesn't matter. How fast would I have to throw a ball to make it leave the Earth and never come back? What speed would I have to give a rocket so it can leave the Earth system and say fly to Jupiter? the minimum velocity to break Earth's gravitational pull and go explore the solar system. Now for this one, it actually takes calculus to derive the escape velocity, so I'm not even going to walk you through it. If you go to the unit 1 part 3 slides, the supplemental part, I go through the calculus derivation. If you're curious, there's lots of really, really cool supplemental information. I highly recommend going to check that out. But let's actually take a look at the escape velocity equation. It's the square root of 2gm over r. Wait a second, that's the square root of 2 times the square root of gm over r. That's the square root of 2 times the orbital velocity. Square root of 2 is 1.41, and then some other decimal places. So call that about 1.41, 41% greater than the orbital velocity. So you can go and calculate that out. How fast would you have to launch a rocket? What speed do you have to get it up to so they can leave the Earth forever? You can plug in all the numbers if you want. You can independently check it if you like working with equations. You'll get a number of 11.17 kilometers per second is the escape velocity for the Earth. And notice it has the same dependencies as orbital velocity. The mass of the Earth and the distance away. Increase the mass of the Earth, I would have to throw this at a faster velocity to make it leave and forever come back. That makes sense. More mass, more gravity. I'd have to throw this harder to make it leave. If I'm launching from a higher distance, if I'm launching from further away from the Earth, a bigger distance, a smaller escape velocity, it's easier to launch things from orbit. If you're already up in orbit, you've already spent the energy to get up there, it's easier to keep going. A rather interesting way to reverse this question is, let's imagine we have something that's not in the Earth system and is to come visit the Earth system, maybe an asteroid. That asteroid coming from out of Earth orbit and then to Earth, the minimum velocity it will impact the Earth will be the escape velocity. It'll have more than that, but that's the lowest velocity of anything that's going to impact the Earth that's coming from outside the Earth system into the Earth system. Scary stuff. I don't want to imagine something that's like 10 kilometers across, or even a kilometer across, screaming in, moving at 11 kilometers per second to hit the surface of the Earth. Okay, so that scary thought aside, I just want to show you some examples for this, and I'll let you get some practice in the homework on questions that you might see. But I just want to go ahead and show you how this all works, because this is all for the curious. That's why I made this entire thing green, but this is some real practical applications. These are the things that NASA scientists or NASA engineers that are designing our rockets and doing mission design are constantly thinking about. If we want to go to the moon of Jupiter called Europa, how much velocity do we need to give our rocket? So to escape the Earth, this is the same as thing that I had on this slide, except I crunched through the numbers for you. You can calculate the escape velocity is 11.2 kilometers per second. But let's imagine that we build a launch station that's already in orbit. So we'd launch from the same altitude that the ISS is at. So just above the surface of the Earth, about 400 kilometers up, let's imagine that we build a space dock, a space station, there, so we can launch things from there. Well, we're 400 more kilometers away, so I can add that to Earth's radius. Just add 400 kilometers to this number right here. And notice that if launching from the International Space Station, it's 10.8 kilometers per second. Less. I move further away from the surface of the Earth, and if I want to consider the escape velocity from that point, the value is smaller. Now let's talk about, let's say that we have something that we put in the same orbit that the moon has. Not saying it's on the moon, but it has the same orbit that the moon has. So it's orbiting the Earth at a distance of 1.3, or it's, oh, sorry. Different question, sorry. Back it up, Dr. Lindsay. It's the end of the week. Okay, so what if we wanted to build a moon base and launch from the surface of the moon? The moon has less mass than the Earth does. So it should be easier to launch from it. It does have a smaller radius, and those two will balance out. But just for the curious, why might we talk about building a lunar base and using that as our launching station to explore the solar system? Well, let's look at the escape velocity for launching from the surface of the moon. I can plug in all the correct numbers, calculate it out, 2.375 kilometers per second. Almost a full 10 kilometers per second lower. And whenever you're talking about how do we get things up to speed, we're talking about the amount of rocket fuel you have to use to bring something up to speed, to accelerate it to the escape velocity. That is an enormous saving on the total amount of rocket fuel. It is super easy to launch things from the surface of the moon compared to launching them from the surface of the Earth. It's much easier to escape the moon than it is the Earth. So eventually we may want to consider building all of our space exploration, our solar system exploration facilities from a moon base. I know we're talking some sci-fi stuff there, but these are things that people actively think about. And now you can see why that would be such a huge advantage. Okay, I wanted to end some of that complicated topic with some kind of cool, fun applications. Hopefully you know a little bit more about how we orbit and how we launch rockets to go explore the solar system. And I will see you in the final video where we're going to put everything together so we can finally understand Kepler's 3 laws of motion. I will see you when we crack the secrets of our solar system.